Okay, so today what we're going to do is use Google's GraphCast model to predict the weather over 10 days in late 2023. And we're going to compare that to other predictions that are out there with the aim of being answering the question like, is GraphCast any good? Is it good? Is it bad? What's the deal? So that's the plan. If you haven't heard of GraphCast before, you are missing out, my friend. It is a model that Google made to predict the weather. It's based on, the input is the reanalysis data from the European Center for Medium Range Weather Forecasting. So that's a fun little name for you, ECMWF, I believe. And so it takes the European Weather Forecasting Agency creates this, the ECMWF creates this reanalysis data, which represents how the state of the weather was at a given point in time. And then that gets fed into GraphCast, and then GraphCast can make predictions of up to 10 days. And the really significant, interesting thing about GraphCast is that its predictions are about as good as the predictions that are made by the big supercomputer that the ECMWF has, even though you can run it on just something like 24 gigabytes of RAM. So that's really cool. Presumably, in theory, this is like very democratizing. Now, I thought this was great, and I was trying to use it myself, and I had a lot of difficulty. I had huge amounts of difficulty actually getting predictions, and then once I had the predictions, loading them, and then interpreting what the hell they actually meant. So this is a tutorial on all of that. We're going to go, from start to finish. We're going to start with the dates we want, and then from that, we're going to make predictions with GraphCast, and then we actually compare it to some data that we're pulling from elsewhere. And ultimately, at the end of the day, we're going to end up with this graph, and then we can, plot some more things, and it's going to be fun. It's going to be fun and good. That's the plan. So without further ado, let's get to the top of this goddamn notebook, which again, you'll find in the description. Essentially what we're going to do is, because my computer's not big enough to run GraphCast, and probably neither is yours, we're going to spin up a run pod. So we're going to use this GPU provider online called RunPod. And we're going to run GraphCast on one of their machines, and then automatically spin down the machine, so delete the machine. And we're also going to save the outputs to Amazon S3. So at the end of the day, you'll just end up with the outputs on S3, and then you can pull them down and do what you want with them. The outputs will be like 8 gigabytes worth of data, so like huge outputs. This is why it's sort of hard to deal with them locally. So that's the process. We're going to create the forecasts, we're going to download some other data to compare the forecasts to, and then we're going to, come to a conclusion, like, is it good, is it bad? That's how it's going to work today. So first thing, we're going to install some dependencies, and the next thing we're going to do is we're going to put all the keys in. So full disclosure, this code uses something that I wrote, a PyPy package. Yeah, here it is. I'm currently maintaining it. And to run this code, because this code is the code that actually spins up the run pod, runs remote GraphCast on it, and then saves it to S3. To run this code, you'll need to give it a whole bunch of credentials. So just be careful. Maybe read my code before you give me the credentials, because maybe I'm secretly saving them to a server or something like that. But I just thought I'd warn you about that. Okay, so what credentials do we need? An AWS key, the two components of that, an AWS bucket name, a CDS URL. So CDS Copernicus is the place where the weather forecasting reanalysis is sitting, and CDS key, which again just goes with the URL, and then finally a runpod key, which will allow you to spin up and spin down runpod instances programmatically. Okay, so first thing, we're just going to go and we're going to collect all of these things, starting with runpod. So runpod, we're going to go to, you make an account. There's the link to how to make an account in the description. There's two links. There's one that is a non-affiliated link, and another one's my affiliate link. If you use my affiliate link, it'll be the same for you, but I'll get some of the money you spend if you spend like heaps of money, which probably you won't. Anyway, I just thought that'd be fun. The amount of money you make working as a data scientist makes this kind of stuff not really worth it. But I just thought, hey, maybe if a lot of people sign up, then I'll want to do more in the future. Okay, so you create your runpod account, go to settings, API keys, and then you create a new API key. Let's do it right now. It has to be read and write. Create, and great, here it is. So let's paste that in. And before you guys get any funny ideas, I will be deleting this API key before the end of this tutorial. So yeah, don't even bother. Okay, so that's run pod. Let's just do CDS Copernicus. So if you go to CDS Copernicus, you have to make an account, and I think maybe that'll take a little bit of time. I could be wrong, but I think it'll take a little bit of time because I think they have to like approve you or something. I think it took me like a day to get an account, although I could be wrong. And what you have to do is you have to visit this how-to URL. So API how-to. And once you go to it, it'll show you the URL and your key on that page. So go to that page, API-how-to, and grab the key and paste it back in. I won't be going to that page because otherwise you'll see it. And I don't want you to see my key because I don't know how to reset it. Okay, so that's good. Those are the easy ones done. I'll assume that you've gone ahead and inserted your URL in the key there. Now let's go to AWS. So AWS, just make a new role and give it Amazon S3 full access as a policy. There's definitely tutorials on how to make roles in AWS out there, but just like create a new user and then attach this policy, AWS S3 full access, and now that user will be able to do anything on S3. And then create some security credentials. So you go like create access key. And then you go local code, and then you say I confirm, and then you click next, whatever, which is down here. Then you create the key, and then you download that key. So it gives you the access key ID. Chuck that here, it gives you the actual access key itself. And again, I'll be deleting this afterwards, so don't worry. And then you also have to choose an AWS bucket. So I'm assuming that you have a bucket already. I'll be using a bucket that I already have called Weather Bucket AU, which contains essentially nothing but these predictions. Doesn't have to be an empty bucket. But you know what? Just for the sake of it, we'll create a new bucket. This is called new. Just to show you that like the kind of settings you need, you can just leave everything as default and then create the bucket and it'll just work, which is nice. Great. It exists, new weather bucket AU. And then all you need to do is copy the name of that bucket and then log it here. Okay, so now what I'm going to do is I'm going to put the CDS URL and key in here, and then I'll meet you after the cut. Okay, great. So now all our credentials have been gathered together. That's the most annoying, arduous bit of the process. Now we just need to import our dependencies. A lot of these dependencies are related to loading climate data. This one here is, of course, Remote GraphCast. That's the one that I made. And the first thing we're going to do is actually generate those forecasts. So the process here is step 1, spin up a run pod instance. Step 2, load the correct Docker image for GraphCast to run. Run that image, which will download the reanalysis data from the ECMWF that you can use to start make predictions. Make the predictions on the GraphCast, on the run pod, and then save those predictions to S3 and then close down the run pod. So this remote cast, that's what it does. In this case, we're starting on this date, which is the 22nd December 2023, 6 a.m. in the morning. And we're going to forecast 10 days. Now, if you actually visit RunPod now, you can see that, look, there's this pod now, and this pod is now running, and it's like downloading stuff. It's downloading a Docker image. So we can kind of keep track of it here and make sure everything's going fine. In the meantime, I just want to make a sort of note. You can only do about 10 hours worth of forecasting with GraphCast. So this is about as many hours as you can forecast before it starts getting inaccurate. That's the number it was designed to forecast. And you always have to start at 6 a.m. or 12 p.m. And the reason for that is there's actually sort of a long, complicated reason, but essentially it was designed to only start at those times because of the way that the reanalysis works. So I'll link a YouTube video that explains that a lot more. The actual GraphCast guys explain why that is. But that's sort of important. If you try to start the predictions at like, you know, some other time, like 8 a.m. or 9 a.m. or 9 p.m., it won't work. And the predictions happen in 6-hour increments. So we're going to end up with 40 6-hour incremental predictions at the very end. Okay, so let's check on the run pod again. What the logs look like. It looks like it's still downloading. It's finished downloading the Docker image that I made. If you want to check out the Docker image and just use that, that might be the easiest thing to do, really. This Docker image makes it easy to run GraphCast. And okay, so it's downloaded the Docker image, start container, so the container started. Now we go to the container logs, and it'll be making all these requests to Copernicus to download the reanalysis data that it needs to start the predictions. This can sometimes take a long time because sometimes they'll Copernicus will like limit you. So let's have a look. Copernicus, and if you go to your requests, it'll show you these are the things you've requested recently. If there's a lot of people using Copernicus, sometimes they'll like block you here and they'll put you in like queued. And in that case, maybe I might have to wait for like an hour for them to actually give you the data. But at the moment, it looks like everything's been like granted, it's downloadable. So maybe we won't have to deal with that, which would be nice. Just says downloading. No predictions have started yet because when they start, you'll see the GPU memory to like spike. Oh yeah, and let's talk about the cost here. This is an A100 instance. It takes $2 an hour, costs that much. This is USD. So given this is probably going to take, if we're really lucky, about 10 minutes, it shouldn't cost more than like, 50 cents or so. Okay, great. And now you can see the GPU memory just spiked. So that means that the predictions are being made, which is nice, good, excellent, fun times. Okay. And the upload location will eventually be given to you in this variable here. And after that, we'll just download it. Okay, so I'll cut again to when this is finished. Okay, so it polled for a while, and then it told us, okay, everything is complete. And if you go to this place, you'll find the actual files. So, let's actually check that, see if that's actually the case. So S3, new weather bucket, and it's got a funny name. So new weather bucket, and here we go, funny name, Sylvian Jungle, and great. So this is going to be, that's just a file that I put there to make sure the code knows everything's complete, and this is the actual output itself. So looks good, looks like the file's there. So what we're going to do, obviously, is we're going to download that file next. So we've already got the upload location here. We're going to change that by just turning that into a prefix, and then we're going to use the prefix to download the actual file onto our Google Colab environment. This will take like another 5 minutes because, as you can see, this is like a 6.4 gigabyte file. It's really big, lots of predictions in there for 10 day. And that's because you're not just predicting like a particular variable. In this forecast, you predict like weather, wind speed, you predict temperature at 2 meters, you predict temperature at like 75 meters, and there's like a whole bunch of ranges of temperatures that you predict. The weather's complicated, and that's why we have to deal with these huge files. Okay, that actually didn't take too long. It took like a minute probably. And so now the file is here, and I think we can see it if we look over here. Yeah, that's the output. I'm going to delete this because this is like an old file that shouldn't exist yet. And I'm also going to delete this because this is an old file that shouldn't exist yet. And finally, I'm going to delete this as well. So all we have is the output. And the complete file, which you can ignore. The next portion, we're going to download OpenMeteor data. So this is a website that collates a lot of different weather forecasting and also reanalysis data, and also other kinds of data as well, I'm sure. Seems like a great project. Whoever made it, they're obviously great and really cool. And we're going to use their API they provide, which is a nice, excellent, clean API to get a bunch of points. We're going to choose like 49 different points on the surface of the Earth. And for those points, we're going to get the OpenMeteor forecasts, which I don't exactly know what they're used to forecast, but I think they collate a whole bunch of different forecasts, including forecasts made by the ECMWF, and also just a reanalysis for that time. So the forecasts are forecasts that were made starting from the same date here, so that the forecasts from the OpenMeteor also started at this date, and they forecast the next 10 days. And then we're actually getting the reanalysis data, which is the data that is actually correct for those 10 days. So reanalysis is kind of like observations, whereas the predictions, the forecasts are actually like predictions. Yeah. Reanalysis data, it turns out, it's like you take the observations and then you kind of interpolate between them to work out the whole kind of a holistic view, as opposed to just having like 8 different points of data. You try to make it a whole thing. Okay, and that was really quick. we downloaded this melbgrid.csv file almost instantly, even though we were downloading like 49 different points. So that's great. It's excellent. Now we're going to download some ERA5 data because I don't really know how trustworthy OpenMedia is. Like I don't know much about them. I haven't read about them extensively. They just seem like a good, well-maintained project. So just to get some secondary kind of opinion, we're going to download the ERA5, which is the European Center for Medium Range Weather Forecasting's official reanalysis product. So it's like very trustworthy. This is used everywhere. It's just like a really, really good product. It's what GraphCast uses as its input. And so we're going to take the actual ERA5 over the period of 10 days that we're predicting. Like what was actually happening, and we're going to compare that to GraphCast predictions and also to the OpenMedia predictions. So there's this class here called the state list. It's just to make it easier and quicker to download from OpenMedia because of a bunch of quirks of the API. Sometimes here you'll get screwed because OpenMedia will like deny your request, or it'll keep you going for ages. But it looks like it just completed instantly, if I'm not mistaken. And if that's the case, we should have this file sitting here, 22 ERA5.mc, which, yeah, we do. Okay, great. So that's excellent. We've now got the OpenMedia data, both forecast and reanalysis. We've got the ERA5 data, and we've got the GraphCast predictions. So we're actually ready to go. This is great. So we're going to compile all these into sort of one list of data frames, which you could definitely put it as one big data frame, but since this is the only analysis we're doing, this is fine. So this is my collation function. Interestingly, the GraphCast data, it starts off in this weird format, and it actually almost appears to be a bit broken when I was using it earlier. Maybe they've fixed it by now on the official GraphCast API, but in order to get it to actually turn into an X-array, I had to do a lot of processing that didn't really make much sense. So that was kind of annoying. But essentially what I did is I took the huge ball of data, the 6.4 gigabytes, and I just took the 2T variable, which is the temperature at 2 meters, which is like what you feel, unless you're a very tall 7-meter human. And we're just grabbing the 2T, the temperature at 2 meters, from all of these data sets, from the OpenMedia forecast and reanalysis, from the ERA5, and also from the GraphCast. So we're taking that, and then we're just comparing that variable. And of course, the ERA5 data and also the GraphCast data is given in Kelvin, so we have to make it into Celsius to be like more understandable to humans like us. Okay, so now we're going to do this processing. This might take about 2 to 5 minutes, mostly because of this process here. Okay, nice. So we've got our 49 data frames. To begin with, we're just going to check one of those data frames out and then do a little bit of analysis on it. So this is what the data frame looks like. You have times on the side, and it's all 6-hour increments. So it's like 12 a.m. on the 22nd, then 6 p.m., then midnight on the 23rd, then 6 a.m. the 23rd, 12, 23rd, etc., etc. And then you have the actual temperature of the OpenMedia reanalysis, latitude and longitude of the OpenMedia reanalysis. Then you have the temperature of the OpenMedia forecast. And then finally, you have the temperature from the ERA. And then finally, at the very end, you have the temperature from the GraphCast. Now, you'll notice that these latitudes don't line up exactly. And that's just because we're pulling from different data sources. And those different data sources, they collected data at slightly offset latitudes. So the forecast for the reanalysis from OpenMedia is sitting at, this latitude, which is slightly different from where the ERA and the GraphCast forecasts were taken from, which is this very similar but not exactly the same latitude, right? We're off by 0.002. So because of that, this isn't a super duper fair comparison, but at the same time, it's kind of hard to work out how would you even find a fair comparison? These are two these are two data sources that are very complex, and they're situated in space. We're are pretty happy that we've gotten the amount of overlap we have. The whole point of this is to compare GraphCast to some other reanalysis, some other forecasts, to determine if the predictions we're getting are sensible and even make any kind of sense at all. Because when you run someone else's code, you have to assume that it's not working. You've made some mistake with it, or they've made some mistake, and the outcomes you're getting are not correct. So our hypothesis is that the forecast that GraphCast will have given us will be way off what the reality was. So that's I guess, what we're trying to test here. Okay, so this is what the data frame looks like, and now we'll just plot all four of those pieces of information against each other. Okay, so here we go. We have GraphCast in the red, we have the OM reanalysis, and we have the ERA5 in the green. This is obviously the day-night curve. So you have like midday, and then it goes down to 6 p.m., and then it goes up at midnight, and then it sort of stays constant at 6 a.m., and then it goes down again. It kind of repeats that. You can see it's kind of reversed, like you'd expect it to be hot at midday and cold at midnight. This is because the data I'm gathering is from this latitude and longitude, which is basically Melbourne. Which is basically Melbourne, Australia, from where I live. Obviously, the sun's upside down in Melbourne, so this is what that's causing now. Okay, and now we'll just plot the errors to see what the errors look like. We'll plot the errors against ERA5 because that's probably the most authoritative source of the temperature at 2 meters, than the ERA5. As we can see, GraphCast, which is the green, seems to have the highest errors. The OM reanalysis it seems like it's pretty close, and OM forecast is also pretty close. It's hard to tell which one of those is closer, but GraphCast seems to be a bit higher in error. And let's actually just plot the means, and we'll see the GraphCast, the mean error of GraphCast is about 1.6, whereas the OM forecast is a lot closer, of like 0.8 degrees. Okay, so that's like, it's not wildly off though, right? It looks like these forecasts the GraphCast is generating, they're about half as good as these other forecasts. God knows what's going into these other forecasts. And we kind of just ran it in like 10 minutes on someone else's GPU. That was really nice and convenient. That's pretty cool. Maybe you guys can do something cool with this. Another thing we can do here is generate this sort of like list of tuples where we have latitude, longitude, the error of the OM forecast, and the error of GraphCast. And so for instance, we can just plot the OM forecast error, and we can see that there's a lot of error. There was a lot of error over those 10 days in this spot, but around this area, like, around the edges, there was a lot less error for the OM forecast. Another plot I did was like over different points. So like just randomly selecting points. These have no like temporal relationship to each other. This is just, if you just look at all the errors, how do we look? And basically OM seems to have a lot more of a variance with the amount of errors that it's getting per point, the average error per point. And GraphCast has less variance, but it has higher errors overall. Now we can plot the overall mean. So you'll notice that this is like these are different numbers. This is 0.2 and 0.5, so it looks like the overall mean's a bit closer. This is because we were only plotting for 1 point here. That was the mean delta for that one particular point, this one here. But this down here is the mean delta over all of these points combined. And again, GraphCast is a bit worse, but only like a little bit worse. It's only about like, less than 1 degree off compared to the other forecast. And yeah, finally, we can plot over time what the errors look like. So the errors start off quite, about less than 2 degrees, and then they spike. What we're not noticing, which is kind of interesting, is we're not noticing the error increase as time goes on. You'd sort of expect that as the forecast progresses, it gets less and less true to reality. And that doesn't seem to be the case. I guess maybe GraphCast is kind of increasing over here. Some other resources are obviously you can just use the PyPy package yourself. You can go and download it and just use it in your own code. And there's also a Docker image that's associated with this code. Here it is. And this is probably the most useful artifact for you here. I'll link this in the description. You can just go and pull this down and run it locally, or you can start up another server and pull it and use this to actually run GraphCast and pass in different variables and so on and so forth. Obviously, if you want to contribute to the GitHub, go ahead and do that. If you have issues, chuck them in the issues. Maybe I'll get around to them when I'm finished doing the 8 or 10 things that I'm supposed to be doing in my time. And otherwise, yeah, good luck. If you make anything cool with this, please link me, and I'd love to know about it.